about some different applications of the derivative. Now, the two we've looked at so far is we looked again at some of these Taylor series and Maclaurin series. And then we also looked at, last week, we looked at the notion of stationary points of functions. So local minimums and maximum points and points of inflections of functions. Okay, so we described how we can find the stationary points of a function by solving the equation df dx equals 0, where f is the function. And that these can be classified as well into local minimums, local maximums, or points of inflection in terms of the behavior of the first derivative, or indeed making equivalent statements about the behavior of the second derivative. And these we applied in a number of, optimization type problems. So in the lecture last week, I did questions 9 and 10 here, which were about optimizing certain quantities subject to certain constraints. And then in the tutorials, I recommended that we work on if you look at the final batch of questions in the end of chapter exercises 23 to 27, there's a few more optimization type questions there. And those can all be solved using this concept of finding the locations of the stationary points of a function and classifying. Okay. So if you've got remaining work to do with those, please do use the tutorials to get any help with those that you need from your tutor. So there's a couple of two more application areas I want to look at in the remaining part of this chapter. So those are in the concept of curve sketching and kinematics. Now, I think I might do the kinematics one today, so I'm skipping the curve sketching material. I've written quite a bit. I've done quite a long example on the curve sketching there in the notes. So I think for the moment, I'll just leave you to read through that yourself. There's a long extended example there. It's mostly applied to cases of rational functions. So where rational functions are quotients of polynomials. So one polynomial divided by another polynomial. And the idea of curve sketching, well, I think it was especially relevant before people had computers or graphing calculators easily available. To be able to fairly quickly pick out the key points of what the graph of that function is going to look like. Where it's going to be positive and negative, where it's going to be increasing and decreasing, where it's going to cross axes, and where it might have any undefined points. Now, it's been superseded a bit by the fact that you can just type the formula into a computer, and the computer will give you a nice picture of it. But they're still useful ideas, useful concepts to have. It's still important to understand, how it is, or why and how a function can become undefined at a certain value, and why it's either zooming off to plus infinity or minus infinity, either side of that value. Okay. So I might go through this example and talk through it in detail in the week after the class test. That's in a couple of weeks' time, just before we go on to the final chapter on groups. But I've given quite a detailed treatment of it there. There's a number of steps we go through, a number of facts we deduce about the function that can help us in sketching the graph of it. And then in example 4.11 there on page 52, there's a good worked example where I take this example function and go through all these steps for it, deducing all these facts about it. That all help inform you, give you the good overall picture of what the graph of that function would look like. Okay, but I'd like to go on to this kinematics section today. So kinematics, is as it says here, is the study of the motion of a body without much attention to kind of the physical processes that are causing it. So we're not doing kind of a thorough investigation of physics or anything, but we're just looking at how, say, for the study of a simple point object, or assuming an object's position is represented by a single point, looking at its motion using the concepts of the position, the velocity, and the acceleration of the object. Okay, so these are typically so-called one-dimensional motion problems. So we're looking at something as it moves along a line, okay, which is the simplest case of motion. Now these quantities of position, velocity, and acceleration, and this is where the derivative comes in. Of course, they're linked by the derivative. So if the position of something along a certain line, or its one-dimensional position in a certain direction, if that position is represented by x of t, then the velocity is defined as the rate of change of that position. Okay. And the acceleration, in turn, is defined as the rate of change of the velocity. And really, these are really the only facts you need to know about it, or the main important link between these quantities that can enable you to solve a whole range of problems that are posed about them. Okay. And also notice, since the acceleration is the first derivative of the velocity, that also means it's the second derivative of the position, okay? Because the velocity is the first derivative of the position. Now, there are a whole bunch of equations. So there are a collection of equations. There are a collection of equations linking x, v, and a. And they're sometimes called the Suvat equations. Have you come across these? Yeah, Suvat equations. I don't particularly have a good memory, or don't have a particularly good image of them in my head, but they're fairly easy to reconstruct. They all just come from the fact that position is the derivative of velocity, and acceleration is the derivative of, velocity is the derivative of position, and acceleration is the derivative of velocity. Or quoting those relationships in terms of integration, going the other way. Okay. So I tend to, not try and remember these equations or look them up, but just kind of reconstruct them as needed in each individual problem, just using these links between x, v, and a. Okay. So we'll investigate this by looking through some examples and seeing how the concept of differentiation or integration can help us solve some kind of fairly straightforward problems in this area. And when we're looking at motion under gravity as well, we're going to use the usual value for the acceleration due to gravity. Okay, so gravity is a force on objects here near the Earth's surface, and the effect of the force is to cause the object to accelerate downwards at this rate, at 9.8 meters per second down towards the center of the Earth. Okay. Okay, and these problems are mostly what we call constant acceleration problems. So where the only force at play, or the only source of acceleration, is a constant one, such as the constant influence of gravity, or the constant acceleration effect produced by a motor or something. Okay. Okay, so let's look at the first question, which is the simplest of these ones. So this question says we have a car waiting at a traffic light. When the light turns green, the car accelerates at a constant rate of 6 meters per second for 4 seconds. So what velocity will the car have reached after 4 seconds, and how far will it have traveled? Okay. So, I mean, it can often help to, maybe not so much this one, but just have a little sketch of the problem. So here's our car at a traffic light. We're going to assume it goes this way. So, let's decide that this is the x equals 0 position at the traffic light, and that this is the positive direction. So x will, as the car starts to move and the light goes green, its position will become positive up from 0. So x is the one-dimensional position of the car. Okay. So the position of the car at time t is given by x of t. And we'll also assume that that the light changes to green at t equals 0, okay? So the light changes to green at t equals 0. So we're told that the acceleration a of t is equal to 6, and it's doing this for 6 seconds. So for t between 0 and 6, at least. So a of t is 6. Now we want to find its what velocity will the car have reached and how far will it have traveled. So the relationship we have is that velocity is the integral of acceleration. Well, if the acceleration is always 6, then the velocity is going to be 6t plus a constant. So you've got the constant of integration when you integrate it. Now, of course, a much better expression for this constant is, in fact, it's v naught, the initial velocity. Okay, so where the constant c is equal to v of naught, you see, because when you evaluate the velocity v at 0, you lose the 6t bit and you're just left with the c. And we know what that value is, okay, because the problem says the car is waiting at the traffic light. So at t equals 0, when the light goes green, the car isn't moving because it's been waiting. So it's got 0 initial velocity. So this value is 0 here since the car is waiting until t equals 0. So it has 0 velocity at t equals 0. Okay. So this means that the v of t is equal to 6t. So then we can also get an expression for x of t. The position is going to be the integral of the velocity, which is going to be 3t squared plus, again, another constant. But we know the interpretation of this constant as well. This constant is just x of 0. Where the constant c is x of 0, and this is the initial position of the car. And I think we already decided that that was just the position of the car times 0. Well, we decided that this was the position 0. So we're going to measure all lengths starting from the position of the traffic light. Okay. So this was just decided at the beginning. Okay, the origin was fixed to be at the starting point of the car. Yeah. 0 to 6. What did I say? 6 is the acceleration. Okay, sorry, it says 4 in the question. Yeah, thank you. Yep. So now we have all the quantities. We have the velocity and we have the position. So we can answer any questions about them within this range. So it says, so the velocity and the position after 4 seconds. So we can now just evaluate those functions that we have. So the position at 4 seconds is x of 4. which equals whatever it is, 3 times 16, which is, what is that, 48 meters. And velocity at 4 seconds is v4, which is 24 meters per second. Okay. The second question is maybe slightly more interesting, slightly more, well, just more to think carefully about. Again, a nice sketch of the picture can help quite a bit as well. So we got a student who's running to catch their bus. They're running along the road after the bus, and the bus starts to pull away from the bus stop. The student is 20 meters away from the bus, or from the stop, and he's already running at his top speed of 5 meters per second. But if the bus accelerates at 2 meters per second, will he catch the bus? That's the question. So there's the bus. It's going to go this way. So we can have, say, x equals 0 here. This would be the positive direction of the x-axis. We'll assume it's one of those kind of old-fashioned London buses where you can hop on at the back. So just if the student catches this back point of the bus, he'll have caught the bus. He'll be able to jump on at the back. So here's the student running. Now, we're going to assume that t equals 0 is when the bus pulls away. The bus begins to pull away. So at that point, the student is 20 meters away, it says. And the student is running there with a speed of 5 meters per second. And how's the bus? Must tell us how the bus is moving. Yeah, the bus accelerates at a constant acceleration. So constant acceleration for the bus of 2 meters per second. Okay, so we've got xv and a. But of course, we've got an xv and a for the student, and we've got an xv and a for the bus. So, we'll have xs, vs, and as, and xs, xb, sorry, vb, and ab be the position, velocity, and acceleration for the student and bus, respectively. Half the thing with these kinds of questions and problems is just kind of setting them up correctly and assigning the notation and giving certain values and stuff. So everything is beginning here at t equals 0. So we want to decide if the equation, say, xs of t equals to xb of t has a solution for t greater than 0. So is there some time at which the position of the student will be equal to that of the bus? Take it at the back point of this bus. Now the question says the student's already running at top speed, so assuming the student maintains his speed, the position xs is equal to the integral of vs. Now, the student's moving with a constant velocity of 5 meters per second, so 5 meters per second. So its position, the student's position, is going to be 5t plus c. But of course, a better way to think of that constant, as we showed before, was to think of the constant as x0. It's the student's position at time 0. But that's minus 20, okay, according to the setup of the problem. So x of s is 5t minus 20. And we're looking for solutions of this equation. Xs of t equals xb of t. So we got x of t, xs of t. So now we want to find xb of t. Well, we're told that ab of t is equal to 2 for t greater than 0, that the bus is moving with constant acceleration of 2 meters per second. So that's going to imply that the velocity of the bus is 2t plus v naught. Should be xs. Vb is 2t plus vb of naught, but we're told the bus was waiting at the bus stop, and then the bus pulls away from the bus stop. So at time equals 0, when the bus is beginning to pull away, it's got 0 velocity. So that's just equal to 2t. So that's since the bus was at rest at t equals 0. And then integrating again, you get that the position of the bus is t squared. T squared plus this constant, which is the initial position of the bus. I think due to the setup of the problem, that's equal to 0 as well, because we positioned the origin at the back point of the bus. So this is equal to t squared. Since xb of naught is 0 from the setup of the, well, just from the way we set up these variables. Okay, so we've got xb and xs now. So we should be able to return to that question that we set out. So are there solutions? Are there solutions to xst equals xb of t? I.e., so xst was 5t minus 20, and xb of t was t squared. So is that equation ever true for t greater than 0? Well, this is just we recognize this kind of thing. It's a quadratic equation. It's a quadratic equation, but it's now you all know that the quadratic equation has a solution some of the time, well, has a real solution some of the times it doesn't, and that's determined by the value of the discriminant, which is the square of the coefficient of t. So it's 25 minus 4 times the product of the other two coefficients. So this is minus 4 times 20. So the point about that is it's got a negative discriminant. So therefore, it doesn't have a real solution, because that negative discriminant is, you're supposed to take the square root of it for the solution. But if you're looking for a real value of t, well, you can't take the square root of a negative real number to produce another real number. So a quadratic equation with negative discriminant, and hence no real solution t. So the student does not catch the bus. Is that okay? Any questions or clarifications on that? And you could ask a follow-up question. How fast would you need to be running? Assuming you would reach some top speed, how fast would you need to be running in order to catch the bus? I mean, is this a reasonable question? Well, that question turns into, you know, what velocity of running for the student is needed so that this quadratic will have a solution. Now, the reason it didn't have a solution was because the discriminant was negative. Now, what was generating the discriminant? Well, it was the initial position of the student, 20 meters away. Well, we'll assume that that's still the case. But the other thing which was influencing the discriminant was this velocity term, 25 here, and that comes from the square of 5. Now, what was the 5? The 5, well, if you trace it back and ask what the 5 did, the 5 was the 5 meters per second, which was the top speed of the student. So we need to see what the lowest velocity is. The lowest velocity Vs is to give a non-negative discriminant. Non-negative discriminant. So the discriminant was, well, it was minus Vs all squared minus the 4ac minus 20 equals 0. Well, if the smallest velocity for which there will be a solution to the quadratic is when the discriminant is 0, when it gives the first time it gives a non-negative answer. So i.e. the Vs squared has to be equal to 80. So Vs has to be the square root of 80, and 80 is 4 times 20, so it's 2 times root 20 meters per second. Actually, 4 times root 5 meters per second. Now that is approximately, got it down here, 8.94 meters per second. Is that a reasonable speed for a student to be running? Well, 8.94 meters per second is equivalent to covering 100 meters in 11.18 seconds. Which, anybody here can run 100 meters in 11.18 seconds? Well, the question setup says the student's already running at their top speed. Yeah, so that was the way we set it up. The student was kind of, already at the top speed. They couldn't go any faster. I mean, it's not out of the question. I think if it was a female student, I think they'd probably have a professional career as a sprinter. I think if they could do 100 meters in 11.18 seconds. Certainly. I'd hazard a guess that nobody in this room could do it. Anyway, okay. So there's a third question there. Question 3. This is one of the ones involving motion under gravity. First question says, suppose you're at a window 18 meters above the ground and you want to throw a stone out the window so that it will be in the air for exactly 3 seconds. How should you throw it? Well, we'll assume here for a start, and it's not too bad an assumption, since you're throwing a stone, something like a small, very dense, heavy object, that will ignore air resistance. So we'll just assume we won't take account of the resistance to motion put up by the atmosphere itself, which for a small, dense, heavy, round stone wouldn't be too much of an assumption. So here's your hand sticking out the window. And if you want the stone to be in the air for exactly 3 seconds, you're either just going to drop it and let it go. Maybe that'll be exactly 3 seconds. Or maybe it'll take too long to fall, longer than 3 seconds, in which case you'd have to throw it harder towards the ground to speed it up. Or maybe if you just dropped it, it would drop in under 3 seconds. So if you want it to stay in the air for 3 seconds, you'd have to chuck it up a bit. So it spends a bit of time going up and then falls down. So the question is, do you throw it up or do you throw it down, or do you just stick your hand out the window and let it go? Well, so there's a constant acceleration of 9.81 meters per second, which goes down in the down direction. So whether that's positive or negative depends on how we're orienting our scale. But if we put our x-axis here, it's pretty conventional to have the ground at x equals 0. And we'll have this as the positive direction, say. So we can say that we're at 18 meters above the ground at time 0. So in this case, then the acceleration has to be a negative quantity, because it's going in the negative direction of the x-axis that we've set up. So if we were to throw it up, this would correspond to a v naught, v of 0 being positive. If we were to throw it down, that would come about from an initial velocity being negative. If the initial velocity is exactly 0, that's just holding it out and letting it go. So the stone is released or thrown, we'll say at time equals 0, t equals 0. So the velocity of the stone at time t is the integral of the acceleration, dt. So that's minus 9.81 t plus v of 0. We don't know what v of 0 is. That's what we're trying to ascertain. Are we going to chuck it up, throw it down, or just have v naught equals naught? So we just leave this as v naught for the moment. The position at time t will be minus 9.81 over 2 t squared plus v naught times t plus x naught. These are constants of integration that are coming in, but I'm naming them as v naught and x naught because that's what they are. Now x naught we do know x naught is 18, isn't it? Because the stone begins 18 meters. So again, we've got this kind of quadratic expression for for the position of the object. Okay, well, whatever you do to the stone, initially it's going to have a positive position because it's starting out 18 meters above the ground. Its position might increase if you throw it up. It might decrease if you release it or throw it down. But anyway, after a certain amount of time, its position is going to be definitely going down. Okay, it's because this minus term in front of the t squared there, the acceleration, the constant acceleration of gravity is going to pull it back down. So the question is we want to arrange that x of 3 equals 0. So after 3 seconds, its position is 0, so that it hits the ground after 3 seconds. Okay. We want to arrange this. So what v naught gives this? Becomes the question. Well, here's our expression for x of t. There it is, and it's got a v naught in it. So we should just substitute t equals 3. So it will give minus 9.81 over 2 times 3 squared plus v naught t plus 18. So it's just becomes about kind of rearranging that and showing, sorry, this is v naught times 3, because t equals 3. And we want this to be 0. So this is going to imply that v naught is 1/3 of negative 18 plus 9 times 9.81 over 2. You stick those over the side and divide by 3. So you get a value for v naught, which is whatever it is. I mean, you could evaluate, I mean, is it positive or negative? It's certainly positive. It's minus 18 plus 9 times 9, so, or 9 times 4. 9 times 5 approximately, but it's definitely positive. So you definitely need to throw the stone up. So the stone needs to be thrown upwards. Needs to be thrown upwards at this v naught, this initial velocity, to achieve this. Okay, gone over a few minutes there. There's a bunch more of these types of problems in the end of chapter exercises. We find questions 19, 20, 21. There's a few more there for you to have a go at. Okay, so we'll end it there for now.